Hi everyone, in this part of the video I want to review some commonly missed questions from the homework. So basically everyone did really well on the homework overall. I'm just going to highlight some commonly missed points from each question. So let's start with question number 1. So for question number 1, many people did really well on this. I'm not going to show how to actually calculate the final answer because I don't think almost no one had problems with that. You all know the t-statistic formula. I want to talk about a couple of kind of higher level problems. For many people, they did not adequately set up the null hypothesis or the alternative based on the context given. The null hypothesis here, reading what the text says the cases can only be distributed to retailers if the bottles have a mean quality rating of above 8. So what that means is that our null hypothesis, it's natural to set it at exactly equal to 8. And many people wanted to set it at 8 or smaller. The problem with that is that that doesn't actually give our sampling distribution a center. So let's plug this material into the online stat book here. This is a handy way to calculate things online. You can also draw it, of course, but this is helpful. So let's say the mean of our sampling distribution is 8, and the standard deviation from the problem should be the standard error, so that would be 0.4 over square root of 15, I think. So let's actually just plug that into stata. So we can write display 0.4 divided by the square root of 15. So approximately this value here. Let's just say we pick the, let's do 0.1033. So we'll come here and come here and 0.033. Okay. Now we're interested in values that are, say, above 8.2. So this will give you the, whoops, that's 8.5, 8.2 here. So we get a value here that is smaller than the one-tailed test for significance, but it's actually larger than the two-tailed test in this particular case because we need to allocate 0.025% of the area under the curve here and 0.025 here. So one thing to consider is, would your answer be different if you changed the directionality of the test? That's the thing that came up a couple of times. But maybe more perniciously, notice that if we shift the sampling distribution, let's say we shift it now to 8 or below, let's say we pick a value like 7, notice that now we have strong evidence that the actual mean is larger than 7, but that's not actually a relevant alternative to us because our alternative of interest, or our null of interest, was that it was exactly equal to 8. And sometimes people worry about this because their idea is, well, if it's bad if it's less than 8, then don't I need the null to somehow include that information? The answer is no. First of all, if you do try to include that information, you don't have a fixed center of the sampling distribution, which is problematic. Secondly, because you're only interested in one alternative, whether or not the mean is larger than that, you can just say, if I find evidence, as we do in the second part of the problem, that it looks like the mean is actually smaller, okay, that's fine. We can just say we're only interested in evidence that it's larger and fail to reject the null, even if we have evidence that it's in fact much smaller than 8. And then we still come to the same conclusion, which is that we fail to reject the null, therefore we shouldn't ship the beer. So that's actually a completely fine way to go about it. By the way, let me show you a couple of things in Stata that are useful. If you want to find critical values in Stata, you can use the function t or invt. So one thing you can do is say, let's come up with a critical value, for example. So we can write invt for inverse t. Then we put our degrees of freedom next. Here that's 14. And then we put our cutoff values. So if we're doing a one-tailed test, as we should, we can just do this. This is going to give us the value of t. It's an inverse function that has 5% of the area under the curve to the left. Then we'll just take the absolute value because we're doing an upper tail test. And we're going to see that we should have 1.76. Then we could do the same thing too for a two-tailed test. And as I mentioned before, we'll actually see a change in our answer here. It's 2.14 and change. We can also calculate our result in Stata too. Let's just pull this up here and we can write, oops, sorry, that's a couple things there. This will be the denominator, and the numerator, we can just say for this problem, of course, that's just 0.2 here. And you can see that we're actually between these two values, which is interesting. So we reject for a one-tailed test, we fail to reject for a two-tailed test. We can also use Stata's t-test immediate syntax. To find out what that is, you can just write help t-test. And notice that we have this immediate form of the one sample t-test. We can just copy paste that syntax here. And it says t-test I observations. Okay, we had 15. The mean. Okay, in this particular case, that actually means the mean we want to test, so 8. It's going to give the same answer, more or less, if we swap them, but easier to not swap them. Standard deviation, we had 0.4. And then the value we actually observed was 8.2. And you can see here, we have this nice thing. If we have a claim that the, oh, sorry, I actually swapped the, see, I actually swapped these. I don't often use this. So here, actually, we're supposed to put, in place of the syntax, let's come back here, syntax, mean, and then value. We actually want to put the mean, the thing we observe, and the value, the thing we're testing. So just to make it, same result's going to obtain, but just to make it easier, let's say 8.2 here and 8 here. Okay, so now you can see if we have an upper tail test, we do fail to reject at alpha of 0.05. If we have a two-tail test, we, did I say fail? If we have an upper tail test, we reject at alpha equal to 0.05. If we have a two-tail test, we fail to reject at alpha equal to 0.05, as I mentioned before. And so we're kind of right on that cutoff. That was something else people missed points on, was not justifying why they did the test in one particular way or another. Okay, let's move on a little bit. So some people on this part B changed the alternative hypothesis to reflect the direction in which the data actually lean, which is that it's smaller. That is not justified in part because in the frequentist paradigm, you can't peek at the data, so you shouldn't set the direction of your test based on what you observe, as Professor Gerber mentioned. Also, it's just not relevant, really, because what we care about is whether or not the beer have a quality rating above 8. So even though it might be interesting to know that if they're 7.8 and they had a standard deviation of 2, of course we can infer from what we saw before that that's going to be significant. Let's do this actually in the online stat book. So we can say standard error here, we need to calculate that. So let's write display 0.2 divided by square root of 15. That's this here. So let's write 0.0516. So we have a tighter standard error here, but the same raw difference. So it's going to be even more different. And let's say we just have outside, we'll do a two-tail test here. So two-tail test would be 7.8 and 8.2. So basically just getting the statistic on either side. Notice that this has a much smaller p-value, right? So we do have significant evidence in this case that the mean is not 8. We have evidence that it's smaller, although technically we just did a two-tail test, and you always have to be a little bit cagey in that situation because technically all we have evidence for, based on how we did the test, is that it's not equal to the value we supposed. But the idea here is that we actually don't really care about that directly for this problem. Okay, so that is essentially the quality rating for the beer problem, and I think that mostly exhausts the sorts of things people had trouble with here. Moving to the next one, the political analyst question. Most people had a pretty easy time with the confidence interval. If you want to know why we use p times 1 minus p, or p hat times 1 minus p hat in the estimated version, over n for the sampling variance of a proportion, you can see my text, where do standard errors come from? I'm not going to get into that too much here. Now, this is a fascinating question. Based on your poll, what is your prediction for the outcome of the election? I would say about half of you said that you still thought Moneybags was going to win, even though this interval was something like 48 to 61% or something like that. From one standpoint, that is not a bad idea, because the idea you all had, for the most part, was that most of the possible proportions are therefore above 50%. And so in some sense, summing up all of those possible proportions, more of them would be a win for Moneybags than a lose. And therefore, we should say, Moneybags is probably going to win. Or some people simply said, even though it could be 48 or 49, it's 55 actually, and so I'm just going to say Moneybags would win. That's not actually great reasoning, with no offense meant, because then it's sort of like, why do a confidence interval? You're just looking at the mean in the sample, but you're not really accounting for the sampling noise. So that isn't right. But the more interesting question, though, is what do we do with the fact that the confidence interval is mostly located above 50%? In other statistical paradigms, like the Bayesian and the maximum likelihood paradigm, we can go a little bit further and use that information. However, that gets much more complicated. And in general, this class and the sequence at UW is part of the frequentist paradigm in statistics, which is generally a little bit simpler. And what that means then is if you want to think about it like this, when people say, the total number of possible proportions that we could have, like we're trying to make a guess about the probability based on the data. So if you want to write it out, you could actually write something like P of the null hypothesis proportion, so H naught. I'm just typing this in Stata. You shouldn't actually run this because it won't run. But you're actually asking a question about the probability of the null hypothesis given the data, right? Conditional probability. However, in the frequentist paradigm, what you actually have information on is the probability of the data given the null hypothesis. It's the inverse conditional probability. And that means that you can't actually directly make a claim about the probability of some null hypothesis, such as it's exactly equal to 0.5 or 0.6 or something like that. All we really say when we find a p-value is this is the probability of the data given the null hypothesis, something that's often elided. So all we're really saying is based on some kind of assumption. So in this particular case, you can think about a confidence interval for proportion as basically saying our data are within plus or minus 2 standard errors of the mean for this particular range of values, meaning that this is not a freak coincidence for the following range of values. Now, in some sense, it is true that more of the values in this particular case are winning for Moneybags than are losing. However, if the idea is we just observed this one draw from the random variable, the sample proportion, you could completely say on that basis, yeah, maybe this is just a really unusual circumstance. We don't actually know. That's the thing. So we don't actually know with any certainty at all that we don't have just a weird sample, right? There's, in some sense, a small probability before we drew the sample that we would have a really weird sample. We don't actually know that. All we can really say with a confidence interval is on the assumption that we don't have an extremely weird sample, here's the range of values that are compatible. One way to see this that I think is helpful is to actually do a test of the null hypothesis, so turn it into a test, that the true mean for Moneybags is, let's say, 0.49, right? So the way we could do that is to just use our standard formula. Okay, now remember a test of the null hypothesis with a proportion, we use the null hypothesis value in the standard error. So we can just write display, our observed proportion was 0.55 minus proposed proportion of 49, and then divide that by the square root of, we're going to say 0.49 times 0.51. You can just write this out. You don't actually have to solve for that, of course, or you can solve for it mentally is what I mean. And then the number of voters was 210. Okay, so that's the idea here. So, by the way, the 0.55, presumably everyone knows that that's just 110 divided by 200. I probably should have spelled that out. Okay, so we get this value here. This is a z statistic. And if we're using a conventional 95% confidence and therefore an alpha of 1 minus c equal to 0.05, we know that this is not statistically significant. We could actually go punch it into the online stat book and look and see. So this is the z-score, so it's on a standard normal curve. And let's say we were doing a one-tailed test. So we want to find the area, let's say above our statistic, which is 1.7 basically. So we would see results this large or larger. Oh, sorry, I did that a little bit silly. It would be significant for a two-tailed test or a one-tailed test. What I meant to say was for a two-tailed test. So let's say we have outside negative 1.7, whoops, negative 1.7 and 1.7. You can see that this would be something of an unusual coincidence, but it would still be a 9% freak coincidence if we had an actual mean for 49%, i.e. Moneybags is losing. So that's the idea, is that the confidence interval actually has to agree exactly with a two-tailed test, meaning that since 49% is in the confidence interval, which is always two-tailed in a sense, since we get the confidence interval by just adding and subtracting two standard errors, that means that if something is in the range of the confidence interval, like 49% is in the range of the confidence interval for roughly two standard errors, that means by definition our sample mean is within plus or minus two standard errors of any value in the confidence interval. So if we have to, by definition, reject or fail to reject, the idea that our observed mean is different from any value using a two-tailed test of the mean that we are supposing, basically. So a confidence interval really is a way of doing a two-tailed hypothesis test. You can see my notes, again, if you go to the syllabus. Oh, I didn't pull it up. Basically, if you go to you may find this useful, to look at week 1 syllabus. You should also just download the syllabus, but again, this is where you find it. If you go to resources, you can see kind of a lot of clicking around here, but basically you can see my confidence interval slides. I think they are, lecture 11, I think. Nope. Sorry, folks. Yeah, so we've got sampling distributions and we've got confidence intervals here. And you can also access my old slides, which are probably even a little bit gentler, from SOC360 Spring 23, and these are actually labeled too. So you can find the confidence interval lecture, if these will indicate what they are. It's one downside of numbering everything. Okay, so I think in these, this is probably where we want. Yeah. So you can see some visual demonstrations of how confidence intervals really work that might be useful to you. Okay. I also wanted to mention one more thing in the homework, which is that a lot of people asked, do I really need to find p-values once I find critical values? The answer is no, because if you have the critical value that you want and then you have your observed statistic, then because the z and t distributions are monotonic on either side of their center, which means basically if you start at the center and you go in the right or the left direction, they only ever get smaller or stay the same value. What that means then is that if you know your critical value is smaller than your observed value, that means by definition the area under the curve from your value to infinity is smaller than the area under the curve from the critical value to infinity, and thus your results are significant. So you don't need to actually use p-values, although you can, and it's helpful to know. So it's actually best practice to report p-values just so you don't use an arbitrary decision criterion. But technically, if you're just doing accept, reject, you don't need to actually give p-values. Finally, one more thing. Sorry, there was a ton of stuff to say about this. Lots of people said the reason that you use a t-statistic rather than a z-statistic is that in some cases you have a small sample, in other cases a large sample. Very common misconception, but let me just briefly say the t-statistic you use because when you write out your t-statistic formula, so you have, again, I'll just type in this data here. So t, of course, is equal to y bar minus, mu naught over s, let's write this in parentheses, over square root of n. So when you do this, basically, you've got a ratio of random variables. Remember that y bar is a random variable. It varies from sample to sample. And s is a random variable. It also varies from sample to sample. So when you have a ratio of random variables that behaves differently than a single random variable, if you write out your z statistic, right, for a proportion, so you have something like this, p hat minus p naught over square root here of p naught times minus p naught over n. Notice that here, because, as discussed last week in class, in this particular case, you don't have actually a random variable at all in the denominator. You assume that the value for the for the population proportion is p naught, then that actually directly determines the value for the standard error under the null. You now don't have a ratio of random variables, you just have the one, you just have p hat. And the same actually applies when you do a CI too. So CI equals p hat, let's just do one part of it, so the lower bound is p hat minus your critical value, so c times the standard error. And now these change to p hat because we don't have a null technically, but we still only have one random variable. So that's why we still use the z distribution. So it doesn't directly have to do with sample size, although the t approximation is important to use when you do have a small sample size, but it has to do with the ratio of random variables or not. Okay, the chi-square statistic, I think everyone had a pretty good time with that. Again, you can see my slides if you want to see a little bit more. Let's try to open this again about, sorry, I wish these would give me a little bit of a display preview. I think this is the chi-square, yeah. If you want to see a little bit about what that distribution looks like and some justification for why we do this, like why we calculate observed minus expected squared over expected, it's in these lecture notes, but Professor Gerber gives you more or less what you need to know to actually do the test, and you're good. So most people did good on that. Finally, number 4 here. This is another case where people in many situations didn't actually justify the directionality of their hypothesis, which I think based on the problem, you at least need to say why you should conduct a one or a two-tailed test. So that was number 1, is you just need to justify that. 2, people use all kinds of different variance formulas, which is fine. Some people use the formula Professor Gerber showed, other people use a different pooled formula. Some people even use the unequal variance formula. I'll just say this, the unequal variance formula is theoretically justifiable. It just comes from the fact that the sum of, well, really the variance of a sum of uncorrelated random variables. So if you draw these two samples independently, they're uncorrelated. Each sample mean is uncorrelated with the other. Then each one's sampling variance is just the estimated variance, the sample variance, SB squared, or well, here he called them X, and presumably it should be Y. But basically you have, SB squared over NB, SG squared over NG. Those are each individually the sampling variances for each mean. So then to get the standard error, you just take that sum and then you take the root of it. If you want to see a full justification, you can go to my GitHub. This is probably pushing the limit for most people, but you can check out this little document I wrote, basically just based on how I teach 360, where I justify all of these things. So I justify, for instance, how we get the standard error formula, why that works for a proportion, et cetera, et cetera. You need to download this to see the full thing or just click more pages. But basically what I did want to point out was if you actually do a simulation, here I just did it using Python. You can see the notation's a little different, but it looks a lot like Stata. Basically, it turns out that the unequal variance formula actually performs best out of using the options being the unequal formula and the pooled formula if we actually run a little simulation. So if you actually just take the standard error derived from the data, so you just simulate, in this case, 10 or 100,000 samples, trying to get the true sampling distribution, then the unequal formula actually better approximates the empirical variance of the differences in the means as opposed to the pooled formula. So there's a pretty good justification for it. people do disagree on these things. Yeah, that's more or less it. Thanks everyone for watching. Sorry that I was gone, but I'm glad to be feeling better. Hopefully this is a useful lecture.